Hello, my name is Nurilatina binti Ishaq with ID number 19001436. So first of all is the pipe and duct diagram. So this is the drawing of the schematic diagram for the pipe. It is represented by the straight line. However, for duct, there is two types. First is the single duct. This is the schematic diagram for the single duct, where there is an arrow here to indicate the flows of the fluid. And the second one is the dual duct. It is represented by the two lines here and here, and its shape is like a ribbon, where the end of it shows the direction of the flows.
Hi, I'm Atika Shazli, student ID 19001185. I'm going to share the function of pipe and duct. First of all, pipes are mostly in circular shape. They are used to transport substance like liquid, gases, slurries, powders, and masses of small solids to their supporting structures at normal temperature and high pressure. Next, duct differ with pipe in their design. Duct can be circular or rectangular, and they are insulated. Duct is used to transport gases at normal temperature and high pressure. They also deliver ventilation air as part of the supply air. In duct, there is also an exchange of hot and cold fluids, mainly gases.
Hello, my name is Muhammad Al-Imran Mansur, ID 190012887, and in this section, I will be explaining the applications of pipe and duct systems in our daily life. Before moving on to the applications, I would like to explain briefly about the differences between pipe and duct. Generally, pipe has a circular cross-sectional area, which allows it to withstand higher pressure differentials, while duct, which has a rectangular cross-sectional area, are only able to withstand lower pressure differentials. So usually, pipe will be used to transport fluid, while duct is used to transport gases from one point to another. Moving on, these are the applications of pipe and duct flow. Firstly, the use of pipe can be found in the water piping system, which allows the treated water from tank to be transported to the household area. Next, the use of pipe can also be found in the nuclear power plant, where coolant is transported via pipe to the reactor. On the other hand, the use of duct can be seen in the centralized air conditioning system, whereby cool refrigerant is transported into the house while the warmer air is transported to the outside. Last but not least, the applications of duct can be seen in furnace ventilation system, where duct is used to transport exhaust gases out from the chimney.
Greetings, my name is Agnes Inshin Hui, ID 19001155 from Group 2. We are given the question 13 of the tutorial, which is that steam enters a pipe, and we are given the inlet and outlet diameter, pressure, and temperature, as well as its velocity, to determine the rate of heat transfer in kilojoules per second. Before we proceed with the calculations, we have to make a few assumptions, which is number 1, this process is under steady flow system. Number 2, change in kinetic energy and potential energy of the system is negligible. Number 3, there is no work interaction involved. Now we can start with the calculations. First, we pull out the energy balance equation for steady flow processes. From our assumptions, we can simplify this equation. Kinetic energy and potential energy differences are negligible, and there is no work interaction. We can obtain this equation, so to find the rate of heat transfer, we will need H1, H2, and the mass flow rate. Therefore, next, we determine the state of the steam at the inlet and outlet. Using the steam table at the table A4, and the temperatures at inlet and outlet, we can determine that the inlet and outlet steam are both superheated vapor, as their pressures are lower than saturation pressures at their respective temperatures. Next, we look at the superheated water table, table A6. We can see that H2 is at about 2900 kilojoules per kg, while H1 is about 3000 kilojoules per kg. Now we have to determine the mass flow rate. As this is a steady flow process, we can use either inlet mass flow rate or outlet mass flow rate because they are equal. The formula to calculate is mass flow rate equals rho times average velocity times the cross-sectional area, and knowing that the density is equal to 1 over specific volume, we can obtain this equation. Using the inlet temperature and pressure, we can find that the inlet specific volume is 0.12551 meters squared per kg. Knowing that the cross-sectional area is pi r squared, we can substitute all the values and obtain a mass flow rate of 0.4 kg per second. Now we can find the rate of the heat transfer by just substituting values of H1, H2, and mass flow rate Then we find a net rate of heat loss, which is 45 kilojoules per second.
Thank you.